Welcome to our next video on derivatives. In this one, what we're going to do is we're going to take a look at what a derivative means, about tangent lines and some velocity and some instantaneous rate of change. We start out with secant lines. Secant lines connect 2 points, as you can see in this picture, connect 2 points on this graph, and we took a look at the rate of change of the y value over the rate of change of the x value. And that's often referred to as the average rate of change. A lot of times if the AP exam asks you about this, they'll ask you about average rate of change as opposed to the instantaneous rate of change. In my first example, I find that average rate of change, or the slope of that secant line. The -1 to 2 is an interval, so I need to find the y-coordinate. So if I plug in -1 in my equation, I get 0. If I plug in 2 in my equation, I get -3. And then what I want to do is I want to find the slope of that line. So -3 minus 0 over 2 minus a -1. And I end up with, if I work that out, I end up with -3 over 3, which is -1. So the average rate of change on that interval is -1. I don't give you any units of measure, so you don't have to worry about that particular part of it. The next part is, as I was stating in the last video, is that the derivative is going to be the slope of this tangent line to the graph, and we're going to define that in our next video. And as part of that definition, we're going to have this limit, what we call limit definition of a derivative. So it's the limit as h approaches 0 of f of a plus h minus f of a over h. The a value is arbitrary. I could use the letter x, I could use the letter a, or I could even put a number in there, like if I want to find the derivative at 2 or 3 or 5 or whatever, I could do that as well. This is, like I said, I'm going to formalize it as a derivative in our next video, but in this case we're just going to be writing equations of line tangent to the graph by using this limit definition. This will find the slope of that line. We'll not find the equation, we'll find the slope of that line. So like for instance, I have f of x equals x squared, just a little parabola. And I want to write the equation of line tangent to the graph at -2, 4. We'll worry about writing the equation of that line in just a minute. But what I need to do is I need to find the slope of that line. So the slope of the tangent line is going to be the limit as h goes to 0. And then it's going to be a plus h squared minus a squared over h. I then need to algebraically work it out, so it becomes the limit as h goes to 0 of a squared plus 2ah plus h squared minus a squared over h. A lot of algebraic little mistakes right there, so if you have trouble with some of the algebra, just let me know and I'll try to help you out on that. The a's will drop out. Basically at this point, you've got everything that's not divisible by h has to drop out, so you can divide out that h. So when I divide these out, I end up with 2a plus h, and then the limit as h goes to 0 of this statement is just 2a. So now what happens is that to the graph of x squared, the slope at any given point is 2 times wherever that point is. So at my point at -2, 4, the slope of that tangent line is going to be 2 times -2, which is -4. So then writing the equation of the tangent line, we write it in point slope form. It's y minus y1 equals the slope times x minus x1. This is definitely the easiest way to write that equation. So it's going to be y minus 4 equals -4 times x plus 2. And that's the equation of line tangent to the graph. You can leave it in that format. You don't need to manipulate it around. Another concept which is related to it is velocity, and we look at average velocity, and then we also look at what we call the instantaneous velocity, or the velocity of a point that's moving in motion. The average velocity is distance traveled divided by time, and then the velocity at a particular point is that same limit definition. That velocity at a particular point is like when you drive past one of those speed cameras, where right when you drive past it, what's happening? How fast are you going? Is it going to take your picture, or is it not going to take your picture? So if I have something like this, where I have a sandbag that's dropped from a hot air balloon, and I have, the position of the sandbag is given by s of t as -16t squared plus 512, and I'm looking at, okay, what is the velocity at a seconds, and then at 2 seconds, and then the instant when it hits the ground, we'll have to find the time on that one. At a seconds, that's going to be that limit definition. So I'm going to take, for this part, is going to be the limit as h goes to 0 of -16 times a plus h squared plus 512 minus negative 16a squared plus 512 over h. When I algebraically simplify that down, I got to square out that binomial just like I did in the last example. So limit as h goes to 0 of negative 16, it's going to be a squared plus 2ah plus h squared plus 512. I'm going to distribute that negative, so plus 16a squared minus 512 over h. And then finally, if I distribute that negative 16a squared plus 16a squared, those will cancel. So that goes away. The 512s will cancel. So ultimately, I'm left with the limit as h goes to 0, and it's going to be negative 32ah minus 16h squared over h. Go ahead and divide out the h then, and you're going to end up with negative 32a, and then it's going to be minus 16h. The limit as h goes to 0 of that statement is just negative 32a. So the velocity of this particle, the sandbag being dropped at any given point, is negative 32 times wherever, whatever time you're at. In the second part, if I want to know the velocity when t equals 2, I'm going to put in 2 for a, so it's going to be negative 64. In this particular case, I think it's what, feet per second? Yeah, it's feet per second. Sometimes units will come in, so we'll practice on units a little bit. And then finally, if I want to know what the velocity is when it hits the ground, I've got to know when it hits the ground. So I need to take negative 16t squared plus 512 equals 0 and solve it. I did that, and what I got was at t equals 4 times the square root of 2 seconds. So then the velocity would be negative 32 times 4 square root of 2. And again, that will be feet per second. So negative 128 square root of 2, and that's in feet per second. And then finally, the last piece of this puzzle is that the instantaneous rate of change. And again, the instantaneous rate of change is going to be that limit definition. So it's the limit as h goes to 0 of the f of a plus h minus f of a. In this particular case, I'm looking at Ohm's law, and I have this 100 over r, and I want to find what is the rate of change at any resistance r. So it's going to be the limit as h goes to 0 of 100 over r plus h minus 100 over r, all of that over h. We got to work this out, so we've got to do the subtraction of the fractions right here. So common denominator is r plus h times r. And then on top, we've got to rewrite it. So I had to multiply this one by r, so it's 100r, minus, this is going to be 100 times r plus h, and that's over h. Keep on simplifying algebraically, so the 100 r's will drop out on top. So I get negative 100h on top over r plus h times r. And then I'm going to multiply that by 1 over h, because remember, when you simplify a fraction, you multiply by the reciprocal. We're taking the limit as h approaches 0 of that. These h's will now cancel, and now I can let h go to 0. And when h goes to 0, I end up with negative 100 over r squared. So that's going to be that rate of change of the voltage. And then finally, this is at part A, so the negative 100 over r squared. And then the resistance, a resistance of 20 ohms would be negative 100 over 20 squared, or negative 1/4. All right, so this will get easier. You won't have to algebraically work out these limits much longer. this is the last part of this, and then we'll define it. We'll get into some shortcuts, and then it'll get a little bit more straightforward and not quite as difficult to understand. See you in class. Hope to clarify for you.